Hey, how you doing? So we're gonna have a little lesson on something called the integrated rate law, and we will also look at some graphs and learn how we can graph data to determine the order of reaction. And then the integrated rate law integrates time into a rate law equation. So we can talk about what is the concentration after a particular amount of time has passed. So I'm going to go ahead and share my screen, and we will get to topic 5.3, integrated rate laws. All right. And we're getting a couple more lessons on kinetics, and kinetics will be done. As I mentioned, it's a pretty quick unit here. Come on, iPad. There we go. All right, so integrated rate laws, right? And kinetics graphs. We're actually going to start with kinetics graphs, all right? So if what I'm going to do is tell you another way to determine the order of reaction, the reaction order. And we said it can only be determined experimentally. That is true. But we can take experimental data and graph it and determine from that what the order of reaction is, okay? So if the concentration of the reactant versus time graph gives a straight line, then the reaction is zero order. All right. So if you make this graph and you get a straight line and it is concentration versus time, you will have a straight line with a negative slope, and that will tell you that it is zero order. All right. And what that means is the concentration does not affect the rate, right? We've already talked about that. The changing in the concentration doesn't affect the rate. So what we see here is a constant rate, okay? Now, if that does not give you a straight line, then it is not zero order, okay? It won't be zero order if it does not give you a straight line. If it does give you a straight line, then it is zero order. If the natural log of the concentration of the reactant versus time graph gives you a straight line, produces a straight line, yields a straight line. Oh, I missed the word line up there. Straight line. Then the reaction is first order. And guys, we are assuming with this that there's only one. No, I'm not even going to say that. It's first order, okay? I need to add something up there. I'll do it in a minute. So what I would have here is I would have a graph. Over here would be the natural logs of my concentrations versus time. And that would yield another straight line. This would be first order, okay? First order. The slope of this line equals negative K. So we could get our rate constant by getting the slope of that line. Up here, the slope of the line equals negative K. So we could get the rate constant. All right, let's assume that this is first order, but I did not graph the natural log of the concentration. I graph the concentration versus time. I will get a graph that looks something like this, okay? Okay, and that's ugly. I need to clean that up for myself, my ADD, or my OCD rather. I've got both, right? I'm a hot mess. Now, this is still first order, but it is not a straight line because it's not the natural log. It's just the concentration. This is first order. A first order reaction mimics nuclear decay, or nuclear decay is a first order reaction. I'm going to say first order process. All right. Now, what does that mean? That means in a first order reaction, there is a constant half-life. Right? What is a half-life? It is the amount of time it takes for half to react, whether it be nuclear or not. It doesn't have to be not, okay? So if I were to look at this graph here and put some numbers up here, let's make this 100, and let's make this, I'm not going to worry about my scale here, guys. Let's make this 50. Let's make this 25. Let's make this 12.5. And let's make this 6.25. I know my scale is off. I'm not going to worry about that, okay? But if, say I started with 100, well, after one half-life, half of it would have reacted, therefore 50 would have remained. Well, if I were to read down and make up a value here, I would see that my half-life is about 2, and we'll say that our time here is in minutes. So we'll say that it's about 2 minutes, all right? Making this up. And then if I was to go to my 50 and cut it in half, right? That would lead me to 25, read over, and this would have to be about 4 minutes, right? Then if I cut my 25 in half, I would be left with 12.5, and that should read at 6 minutes. And then if I cut my 12.5 in half, I end up with 6.25, and I know my graph is off, but that should read about 8 minutes. And what we see is that every 2 minutes, I don't want to write that down there. I want to write it up here. Every 2 minutes, one half reacts. So what that means, let me move my picture here. What that means is that we have a constant half-life. And any first order reaction will give you this constant half-life. But note, that's when it's graphed just the concentration versus time. On the other hand, if you graph the natural log of the concentration versus time, you'll get a straight line, okay? Whose slope is equal to negative k. Lastly, if a graph of 1 over the inverse of the reactant concentration versus time gives a straight line, then the reaction is second order with respect to that reactant. Oh, let me move myself. Sorry. So we're looking at the reciprocal. If the reciprocal versus time gives a straight line, then the reaction is second order. Okay? So that's going to look like this. 1 over the concentration of the reactant. I'm just putting R for reactant. I noticed up there I changed it to A. I apologize. That's going to give a straight line, and this time we're going to have a positive slope. So this time, because the slope is positive, the slope will be equal to positive k, because k is always a positive value. So we don't have the negative sign there as we did up here where we have the negative k, because we need our slope. We need k to be positive. The slope will be negative, so k will end up being positive. Okay? Now that's really important. Another thing, I'll go ahead and write up here by our first order, under our first order data. move my head out of the way, is that it is important to know for a first order process, T, the half-life time, is equal to 0.693 over K. Okay, so I could determine the half-life or K if I know one of the others. There is an equation for half-life in zero order and half-life and second order, but you do not need to know them. Okay. Now, that is what I mean by kinetics graphs, right? So please, write the notes down and figure out what doesn't make sense or ask me to elaborate, to clarify, okay? Now let's look at our integrated rate laws, okay? Which, as I said in the beginning, will integrate time into them. So we will have three. One's for first, one's for zero, one's for first, one's for second. So let's have our zero order integrated rate law. Okay. And what we're going to have is I'm going to use A at a given amount at a given time minus A initial equals negative KT. That's my zero order rate law. This is my concentration at time T, right? This is my initial concentration. This is my time. And obviously this is your rate law, okay? Now you could easily rearrange that and say that the concentration of a particular time is equal to negative KT plus the initial concentration. It's written like this on your equation sheet that AP gives you. So if it is zero order, just as the zero order graph deals with the concentrations versus time, the zero order rate law deals with the concentrations versus time. Excuse me. Let's look at our first order rate law. Okay, so our first order rate law is equal to, so this is what my brain does. The first order graph is the natural log of the concentration versus time. So the first order rate law is the natural log of the concentration. So I'm going to change this to the natural log of the concentration at a given time minus the natural log of the concentration initial equals negative, because it has a negative slope, KT. All right. We could rearrange that to say the natural log of A, or the reactant, at a given time equals negative KT plus the natural log of the initial concentration. First order, natural log. Okay? This will be the equation you're given on your equation sheet. It can easily be rearranged. Second order, and this will be the end just about. Second order. All right, let's go here. Okay, second order. Well, second order has to do with the reciprocal, right? If we graph it, we graph the reciprocal here. So I will have the reciprocal of my concentration at time T minus the reciprocal of my concentration initial equals, now I have a positive KT because it has a positive slope. Okay? Now, I can rearrange that to say 1 over the reciprocal at a given time is equal to k times t plus the reciprocal initial. Okay? Once again, this would be what's provided on your equation sheet. Now, so it's important, it's memorization, that you realize that when you graph, let's see, let's just go like this. When you graph the concentration versus time and you get a straight line, it is 0 order. So look for the graph that has the straight line. If it's concentration versus time, then it's 0 order. Only one is going to give you a straight line. If the natural log versus time gives you the straight line, then it's first order. Or if you look at a graph of concentration versus time and you have a constant half-life, then it is first order. Both of those are given. They give you information. We'll apply this in a minute. Well, no, just know that. You just need to know this. It's on your equation sheet. There's an easy way to get the half-life, right? Now I could get the slope of this line, plug it into here, and get the half-life. Or I could get the half-life from here, plug it in here, and get K. Like there's two different ways to do that, right? This could easily give me K. I'm sorry. This over here could easily give me the half-life, and I could plug in the half-life and get K. Or, as I just said, I'm repeating myself, or I could get the slope of this and plug it in for K and get the half-life. All right, so you need to be able to manipulate that data, and you'll have chances to do that. And then lastly, 1 over the reciprocal is our second order, and it would give you a positive slope. So we have a slope that equals K. K has to be positive. Then we've got our rate laws, our integrated rate laws. Once again, we've got concentration, right? Just the concentration is the 0, right? The natural log of the concentration is first order. The reciprocal, I hope I spelled that right, of the concentration is second. Okay? You need to know that. Got to know that. And look, it goes in oops, bad color. It goes in alphabetical order. So you can try to remember it that way. Concentration, natural log, reciprocal. 0 first, second. Okay? The last thing I'm going to say here is sometimes I've seen students get tricked. It's a messy trick where they tell you that K is equal to, I'm just going to make up a number, 1.5 times 10 to the negative second ms. It's not always S. So make sure you pay attention to, is it seconds? Is it minutes? Is it hours? Make sure you look. Don't assume it's seconds. I keep writing seconds. Now, couldn't I look at this and from this know the order of the reaction? Yeah, because these are the units of a second order reaction, right? So you've really got to know your units for K, because I can sometimes use the units of K to determine the order of the reaction, right? If it says K equals 2.00 per minute, oh, well, this is a first order reaction because that's what the units look like for a first order reaction. Okay, so you need to understand these things. And let me know whatever questions you may have. All right, I have a little bit of time. No, so I'm going to leave that at that. Okay, bye. See you guys later.